Have a look. So here's what I want to kind of hit today. So the assignments. The first assignment was really quick. That was just practicing derivative rules. Second assignment was tangents. What you were doing was writing tangent lines to curves, right? So using the derivative to find the slope of the tangent line, and then using a point and a slope to come up with the tangent line. Yes, ma'am.
Okay, I was doing the first assignment, and I'm confused about the e to the x, because sometimes it would be 0 and sometimes it would just be.
Okay, no, it's not. It's not 0. What you saw there is this question. You saw something like this.
There was an e to the x question in my test, and I was so confused.
Well, yeah, we can do that on the test. That was fine. We weren't taking derivatives of it. That was fine.
Yeah, but I still looked at it and I was like.
Okay, well, we'll talk about that. We'll talk about that. But what you're thinking of was one like this. You had one like, you were taking the derivative, like let's just say y equaled, I don't know, something like sine x plus e to the 11th, right? That one, okay. E to the 11th is what? A number. E is a number, right? E is not a variable. And so probably what you tried to do on that one was you tried to do, when you find y prime, there's the derivative of sine x. You probably tried to do something like that, right? Okay, but what is the derivative of any constant? 0. Okay? See what I'm saying? Okay. And so I put that on there on purpose to kind of try to make that point. Okay? Other questions in the first two assignments? Okay. No questions? All right, here's what I want to do today. I want to just start talking about, and I'll make this assignment for Monday, how about? So it's, so you got a little time to work on some things. I want to talk about derivatives as rates. So this isn't really changing anything. It's not really adding any complexity, but it's just helping you come to an understanding about what a derivative really means. Like if we take, for example, the function, let's just take the function y equals f of x. There it is. If I calculate a derivative of this thing, what does it really mean? If I look at the graph, it means the slope of the curve, right? So if I were to pick a value like a, and I calculate at this point right here at the point a f of a, if I calculate f prime of a, that's just going to be the slope of that tangent line, right? Okay. But if we think about this in terms of f of x instead of y, what are we really doing? If we calculate the derivative, f prime of x is equal to the derivative with respect to x of f of x, right? Another way of thinking of that, if I think of the f of x as being a y, it's dy dx. It's the rate of change of y with respect to x. If the slope at this point, let's just arbitrarily say that the slope of the tangent line is equal to 3. At that one spot right there, what's that saying? That's saying that the slope of that line, I would have to rise by 3 to run by 1 with the function at that point right there, right? So it's giving us a rate, the rate at which y is changing compared to the rate at which x is changing. Think of it in terms of like a physics problem. Let's think of it in terms of velocity. Okay, so if we've got, for those of you who aren't in physics, I'll just give you a real quick explanation. But if we take something, like if we say s of t is our position function. Okay, what's that mean? So you got to really watch this closely here. So if we're talking about a position function, we're going to make this very simple, and we're just going to talk about motion along a straight line. Okay? This is going to be right here at this edge of the board. That's going to be what we're going to define as position 0 on my line. Think of it like a number line, right? Now I'm at position say my steps are always, as a trained physics teacher, are always exactly 1 meter long. And so I'm at position of +2. Now I'm at position of +1. Now I'm at position of -1, right? Make sense? Okay, so if I graph a position versus time diagram, what's that really mean? If I'm going to start here, let's say, and you're going to, it's really crowded up here. Hey, not be so messy. So if I'm just walking along and you're going to start the video camera right now, and I'm just moseying along like this, taking one step every second, then I'm moving to the right, and my position is changing at a certain rate, isn't it? Right? What do you think that rate is? 1 meter per second, right? Does that make sense? If I were to graph this function, if I were to graph that function, my position versus time, well, what would that look like? I started at, let's put some increments on here. So if we look at one frame in that video, I was at a position of -1. Sorry, I was, wrong spot, hang on. My axis is confused. I was at a position of -1. Try that again. That was the first frame of the video, right? So you stopped me right there. Okay. I was at a position of -1 when you start the video, right? So that's -1 meters at time. Put some axes on here. We're graphing S versus T. Okay. So at time 0, I'm at a position of -1. 1 second later, I'm right there. Okay. So 1 second later, I'm at a value of right here, aren't I? Does that make sense? Okay. So my position is 0 when my time is 1, right? Oh my God, I got this, what am I doing? I'm really messing this up. I got my axis backwards. Time and position, sorry. Well, let me start with that. Just block that one out. So at time 0, I'm at a position of -1. How's that? Better? Okay? Well, it doesn't. It just changes how we represent this up here, right? So if I'm right here, if my time axis is the horizontal axis, when we start the video, that's time 0, right?
Yeah.
So my x-coordinate, t-coordinate in this case, is going to be 0, but my position, which we're graphing on the vertical axis, is -1, right? 1 second later, I've taken 1 step, right? So now t is equal to 1, and my position is I'm right at the starting line, so it's right there, right?
Yeah, I understand that, I just don't know
Okay.
why.
Well, it's you'll see why we want to have S up here and T down here. It'll make sense when we talk about the calculus in a second. So 1 second later, at 2 seconds, I'm out here at 1 meter, and then at 3 seconds, I'm right there, right? So doesn't that just look like this? Everybody agree? So if I were to connect that with a function, that function is just something like that, right? That's my position versus time graph, okay? So what if we wanted to look at the rate of change of position, right? The rate of change of position, that's a derivative, right? Whenever we talk about a rate of change of something, we haven't really talked about derivatives that way, but what that really means is a derivative. We're comparing the change in S to the change in T. That sounds like a slope on the graph. And so let's just take an arbitrary time. Let's say at time t equals 2. So right there, if I want to take the derivative, well, what is this equation, by the way, while we're at it? That's a pretty easy line to... Well, you could be more specific. It's the slope is 1 and the y-intercept is -1. So we're going to get a slope of 1 instead of x. We have a t, so I have 1 times t plus my y-intercept of -1. So the position function is just t minus 1, right? But see, that's the equation of that line where we're trading, renaming things. Instead of x, we got a t. Instead of y, we got an s, right? Otherwise, it's the same. if I want to calculate the slope of this, I'm just going to take the derivative. Well, what's the derivative of t minus 1? 1, right? Because I'm differentiating now. T is my independent variable, right? And so I end up getting the derivative as t is 1, the derivative of negative 1 is 0, and so the slope is 1. What that tells me is that the slope of my tangent line right there is obviously 1. Well, it's a line, right? So any tangent line is the line. It's pretty boring, right? Okay, what's that mean though? Well, that's a slope. What are going to be the units of my slope? Think about the units of this. If I'm measuring my position in terms of meters, right? What am I measuring my rate of change of position in? If I make a slope triangle here and I want to find the slope of that thing, I'm rising 1 meter and running 1 second, right? Do I see that? So I'm adding, going up 1 meter, and I'm going to the right by 1 second. If I take rise over run, what does that equal? 1 meter per second, right? Okay, so slope ends up being equal to the rate of change of position, and so that's telling us that the rate of change of position is what we call velocity in physics. Okay? Let's take a little harder picture. Let's make it a little more complicated. That's a pretty boring picture to tell, or a story to tell in pictures. Let's try something like this. So we're graphing time versus position, and this time I'm going to start from rest here, and I'm going to increase my velocity in that direction by the rate at which I'm changing my speed regularly. So after 1 second, I'm going 1 meter per second, but after 2 seconds, I'm really cruising along. Now I'm going 2 meters per second. Everybody get that?
Yeah.
Okay. So what's that going to look like as a curve?
It's going to be some quadratic.
Okay. Maybe something like this, right? So maybe I'm doing something like that. So there's my position function. Starting, I'm not changing my position very fast, but I'm accelerating, and so I'm picking up speed more and more rapidly. Okay? So what if I want to know if that's my position graph? Okay, let's just say that S of t is equal to, let's just say it's t squared. Okay? So at time 0, my position is 0. At time 1, I didn't draw this very well, but at time 1, my position is 1 meter away. After 2 seconds, how far away am I? 4, okay, good. Let's say we want to know out here at time equals 2, let's make it 2, what my velocity is. How could I figure that out? What did I do? So if I'm trying to find my velocity, velocity is just the rate of change of speed, right? So there's my position function, or the rate of change of position, sorry. So v of t is just going to be s prime of t, which we could think of as ds dt if we wanted, right? So rise over a run, that's pretty easy to calculate. If s is t squared, what's s prime? 2t. Okay? So if I evaluate this at 2, what do I get? Voila. My velocity is 4 meters per second. Okay. That makes sense? So we're talking about, whenever we talk about a derivative, we're talking about the rate of change of some quantity. In this case, the quantity is position. Okay? We can do that with other things, though. Let's take an example, like what if we look at something like this? Yeah. That's trademark. It's expensive.
I can trademark it.
Well, because you get it at the Acme store. It's very expensive. Slip rim completely eliminates all types of friction. So if I drop a lead marble coated in slip rim, there's going to be no air resistance. So it's just as though it's falling in the back. It's hard to get, very expensive. So if we coat a lead marble in Slipperium and we drop it from a height of 100 feet, the marble's height, I'm just going to give you what the position function is. The position function is the height of the marble is equal to negative 16 t squared plus 100, where t is just the time in seconds after we drop it. Okay, if you're in physics, that probably looks fairly familiar. All right? So let's do a couple things. Let's maybe graph this thing first. Okay, if I graph the function s of t equals negative 16t squared plus 100, here's what we get. I get something like this. I'm not. I'm using GeoGebra. Yeah. Yeah, kind of.
I don't know how I feel about this.
Yeah.
It's like great value brand.
Yeah. Yeah. So this is, if we graph that function, negative 16t squared plus 100, it makes sense that it's, it's going to be, a is negative, so the parabola is opening downward. The vertex is going to be at 0, 100, right? That all makes sense from previous years. So that's what the curve looks like, right? Okay, well, if we want to evaluate, let's say we want to figure out what the speed is, because this is a position function. I just want to know what the rate of change of this position function is. That looks like a slope, right? So if we graph the derivative function, well, you tell me, what's the derivative of negative 16t squared plus 100? Negative 32t instead of x, right? But t's are a variable. Okay, and what's that going to look like? Well, that sounds like just a line passing through the origin with a slope of negative 32, right? Okay, if I were to, this is all going to be pretty familiar to you. If I were to, where's my tangent line? Right there, I think. So if I were to drag a point along that curve, what is that really representing? So that's representing, like at that point right there, the t is negative, or is positive 0.8. So 0.8 seconds after I drop it, the value of the function is 89.76. What's that telling me? How high is the marble after 0.8 of a second? 89.76. Okay. After, if I drag it along a little further, after a second, it's at 84 feet. After 2 seconds, after 2 seconds, it's at 64 feet, or 36 feet, right? Okay. If we look at the value of that tangent line to that curve, that means derivative, right? Isn't that what derivative, that's the derivative's job, is to tell us the slope of a curve, right? Well, if the slope is negative 64, what do you suppose the value of the derivative function is going to be at 2? Oops. Negative 64. Right? So that's something we've already kind of talked about. Everybody makes that correlation, right? Everybody see that? Okay. So we can use this to do interesting stuff in physics, to solve kinematics equations, if we take advantage of the fact that derivative is a rate of change of a quantity. So let's go back to this problem. So let's do some things here. So let's, first of all, let's find the average velocity of the marble over the first 2 seconds of flight. What does that mean? Okay, so we're gonna look at, think in terms of a video. This is what I would always tell my physics guys. If you're thinking about a kinematics problem, always think of it in terms of a video, and each moment in time is a frame in the video, right? So we're gonna look at one frame of the video is gonna be at time 0, right as we're releasing the marble. The other frame of the video is gonna be 2 seconds later, and we want to look at the at the positions of the marble at those two times, right? Okay, so if we do that, I think I got this set up to do that. I'm pretty sure I do. So there's the point corresponding to time 0. There's the point corresponding to time 2, right? And what's the meaning of that line then that connects those points on the curve at time 0 and time 2? How is that helpful to us? It's going to give us a slope. You're right. What's the big deal with that slope though? Why is that important to us? Okay, we're looking at an average rate of change, right? We're looking at the slope means a rate of change, and we're looking at the rate of change connecting t equals 0 and t equals 2. Let me stretch this thing out vertically just a little bit here. This is bugging me. So I can go, come on. How about if I go negative 80? Okay, that's a little better. Okay, so if I wanted to turn that on. Yeah, the equation of that line, we could find that pretty easily, couldn't we? We've got points at 0, 100, and at 2, and what's the value going to be at 2? At 2, the value of the function is, well, we can find out. 64, we said. We lost 64, so it's 36. Right? If we plug 2 into our function, we get 36 back, right? And so if I wanted to find the equation of this line, I'm just taking advantage of those 2 points on my curve. 0, 100, and 2, 36. That's a little algebra 1. If I want to find the equation of a line passing through those 2 points, I got to calculate a slope. Well, the slope is just going to be the slope of the secant line, because it's connecting 2 points. So we're making a connection here. A secant line is giving us an average rate of change over an interval, right? So the slope of the secant line is just going to be 36 minus 100, which is negative 64, over 2 minus 0, which is 2. And that's 64 feet over 2 seconds. That works out to be negative 32 feet per second. What do you suppose is significant about that? Yes, sir.
Why are we using
Well, I mean, this is the example I picked, just had feet. Yeah, it should probably be meters, but sometimes, you know, we do talk about feet sometimes. So everybody see that that is, and not sneaky feet, I mean actual units of feet. So what do we, what's that tell us here then? That the average speed of the particle, or the lead marble that we're dropping, the average velocity is negative 32 feet per second, right? Is it going that fast at the start? No. What's the instantaneous speed at the start, or velocity, I should say? 0, right? Because the tangent line is horizontal, right? So right when we release it at 0, what do you suppose it is right here? We can find out. It's going to be negative 64, right? And this ends up being halfway in between, okay? So there's our first answer. Right? First question. We know the answer graphically is negative 32. We could easily figure that out without using a graph. That's just going to be the slope of the secant line, which is just going to be s of 2 minus s of 0 over 2 minus 0. Well, there's my position function, right? The position at time 2, we said, was if I plug 2 in, I get 36 minus position at 0 is 100 over 2, so there's our negative 32. And then units, you know, are going to be feet and seconds. Find the average. Oh, I guess I asked you the same thing twice, didn't I? So let's skip down to number 3. Find the instantaneous velocity at t equals 0 and t equals 2. Okay? What's instantaneous velocity going to be in terms of our graph? average velocity is the slope of the secant line. What's instantaneous velocity? Slope of the tangent line, right? That's what a derivative tells us, the slope of a tangent to a curve. I don't know what I did to get so many darn decimal places there.
It's not quite one.
What did I do to...
Is it really that relevant though?
It's not, but it's just kind of a pain. Oh, well, I'm not going to mess with it. I don't know what I did to mess that up, though. Oh, well. I don't know. Oh, there we go. Huh, what do you know? Fixed. Okay, so the slope of the tangent line, we can see right there that the slope is 0, right? It went away, but it's right up there. Go away. Oh, where is it? Slope 0. If I go down here, we can see from the graph, if I get that just right, the slope is, well, there. Well, I'm not quite getting it right, but you get the idea. Slope is negative 64, but we don't need the graph for that. We should be able to do that without the graph too. That's where the derivative comes in, as you told me, right? Instantaneous velocity at t equals 0, that's coming from the derivative. Well, if s of t equals negative 16t squared plus 100, what's s prime of t? Negative 32t. That's the same thing as v of t. That's the meaning of velocity. So v of 0 is s prime of 0, which is 0, obviously. V of 2 equals s prime of 2, which is negative 32 times 2. There's our negative 64. Okay? What if we wanted to ask something... we could do the same thing. Oh, we just did that at 2. Okay, so this asks for speed. Okay, another issue. If the instantaneous velocity is negative 64 feet per second, what do you suppose the instantaneous speed is?
64.
Yeah. Okay, how come?
It's scalar.
Okay, because speed is not, velocity is giving us a direction. So if we go back up to the beginning of the room and we look at our motion along the line, this would be considered positive velocity, right? Because I'm moving in the positive direction. This is considered negative velocity because I'm moving in the negative direction, right? So velocity is a vector. If you're in physics, this is going to make a lot of sense. If you're not, this is probably new. There's a direction associated with velocity, which is important. That's real important. If we're trying to study the position of a particle, we'll soon talk about acceleration, right? Acceleration is an invisible hand pushing you. If the acceleration is in the positive direction, which we'll make sense of shortly in terms of calculus, then that should increase my velocity in the positive direction, right? So the sign is important. If I'm getting an invisible push in this direction, there's a force acting on me, so I'm being accelerated in the negative direction, I should increase my velocity in the negative direction, right? But it also means if I'm starting the video with some positive velocity and I'm getting an invisible push, so a force acting in the negative direction, what's that doing to my velocity? I'm slowing down in the positive direction, right? That's the same thing as accumulating velocity in the negative direction, right? So the signs are important here. We'll talk much more about that later. But velocity has a sign, a negative or positive associated with it. Speed does not. Speed is just telling us what's the magnitude of your velocity. When you're in your car, you're looking at a speedometer, not a velocitometer, right? If you looked at a velocitometer and you went around a corner and you changed direction, everything would go change. Right? If going to Hermiston, I'd have a different reading than coming back from Hermiston. We don't want that. We just want to know how fast is the road going by my car underneath the car. So we measure speed. We don't measure velocity. We don't care about the direction. We just want to know what's the rate at which I'm traveling, right? So moral of the story, make a probably too long a story much shorter. If we want to turn this into a speed, all we're going to do is just take the absolute value, right? Even though the velocity is negative here, the speed will be positive. That's a simple relationship. Okay, we can do something more interesting with that, though. Let's just talk plain old physics for a second. What if we want to take an example like if we were going to shoot a gun off of the top of a building Okay, what if we wanted to know, this is a building, it's a really tall building. This building is gonna be, we're gonna shoot a rifle up in the air, and this building has a height of super high. It's gonna be like the tallest building in the world. It's gonna be 1,000 meters. It's a new building that's not gonna be done for a few years. But it's a kilometer-high building. Okay, that's pretty high. Kilometer-high building. We're gonna shoot this bullet up in the air. What's the bullet gonna do? It's coated with slip rim. What's the bullet gonna do? It's gonna go way up, and then what's it gonna do? Eventually, it's gonna come back down. Okay, I'm gonna tell you what the equation of motion for this is. Okay. The equation of motion, we'll just kind of make this, well, we won't. So the equation of motion, the muzzle velocity of the bullet is 1,000 meters per second. And so here's what the equation is gonna be. Your position as a function of time is going to be, it's gonna be negative 9.8, actually, hang on, negative 4.9. 4.9 t squared plus 1,000 t plus 1,000. Okay? What if I wanted to know how high the bullet goes? Any idea how I could answer that question? I mean, I guess we could graph that parabola, right? But we don't want to do that, right? We don't want to work with that quadratic equation. What could I do? Okay, so here's where we could take advantage of a rate, right? If velocity is defined as the rate of change of position, that's a really easy derivative to take. So v of t equals s prime of t. What is that? What's the derivative of negative 4.9 t squared? T, okay?
Plus 1,000.
Okay? All right, so we have a velocity function. When we're talking about vertical motion, what's positive? Think about the y-axis. Up is positive, down is negative, right? Okay, so the velocity starts off, if I plug in 0 for t, not surprisingly, we get back positive 1,000 for our initial velocity, right? V of 0 equals 1,000. Explain that. Why?
His muzzle velocity.
Muzzle velocity was 1,000 meters per second, right? So right when it leaves the gun, by definition, the velocity should be 1,000. Okay, if I want to know how high it goes, what's going to be happening with the velocity there? That's going to be the point where the bullet comes to a stop and it's going to start coming back down, right? So the velocity is going to transition from being positive going up to being negative coming back down, right? So all we really have to do to find the time when this thing is going to be at its peak would be to set the velocity function equal to 0 and just ask the physics gods, or the math gods, I don't know, I guess maybe these are math gods, what's the value of t that makes that true, right? Pretty easy to solve. I'm just going to get, what, 9.8 t equals 1,000. So I divide each side by 9.8, t equals 1,000 divided by 9.8, which is what, roughly? Somebody tell me, just do it, 1/10 of a second. We got a calculator available there, or a phone or something. What's 1,000 divided by 9.8?
102.
About 102.04. Okay, 102.0, let's say. So 102.0 seconds, pretty darn close. That's how long it takes for this thing. It's coated with slip rim. Without slip rim, it's going to be a lot less than that. But that's how long it takes to get up to the peak of its trajectory, right? The question was, how high does it go? What would I have to do with that time to find out how high it goes? Yeah, this is the position function. Its job is to tell me how high the bullet is as a function of time. What is the value of s of 0? 0 plus 0 plus 1,000. Why does that make sense?
1,000 kilometers.
Because it's 1,000 meters, right, was our super tall building, right?
1,000
Yeah.
kilometers.
Make sense? Okay, so all I'd have to do then is I got to ask the question, what's the value of the position function at 102? And so we just plug that into our position function. So s of 102 would equal what? Somebody real quick, what's negative 4.9 times 102 squared plus 1,000 times 102 plus 1,000?
A really big
Pretty big number. But what is it?
number. Close enough to zero that it's like zero.
No, it's not gonna be 0, it's gonna be real big.
Wait, no, that's height.
Yeah.
Never mind. It's not zero. Let's just keep it with a big number and call it.
Kirk's almost got it.
Wait, don't say it, I want to feel smart.
I was looking up terminal velocity. That guy.
Oh,
What happens if you shoot guys
okay,
down?
okay, now, but is this one's coated with slip rim, so there's no terminal velocity.
But what happens if you just shot a guy down? Would it slow down at terminal velocity?
It would, it would.
Don't
If
do
you
that.
shot a gun down, it would slow down from punch,
I
yeah.
don't know why.
Yeah. Because the air resistance is much, much higher than it much exceeds the force of gravity. Yeah, it slowed down a bunch. What is it?
52,000, 20.
Say it again?
20? Yeah, 24.
0.4 meters. That's how high it goes. Okay, pretty high.
Where? Which one are you supposed to use? I'm so confused.
So we took this, right? If we want to know how high it goes, we just took the height or the time when the velocity goes to 0, which is when it stops going up and it's going to start going down, and plugged it into the position function. Okay?
How did you get that wrong? What the nut? Okay.
Okay, make sense?
So cool. Love that. Love
Okay.
that for you. Love that.
All right, so just as kind of a real quick, how much time we got?
2 minutes.
2 minutes. Okay, so this is a good way to end this, right? So this doesn't give you anything, no homework with this yet. I mean, I got an assignment, but we're not ready for you to start it anyway, so we've got another day to kind of work on homework. What would happen, do you suppose, if I took the velocity function and took a derivative of that? So v prime of t, what would that be, first of all, if I took the derivative of my velocity function? Negative 9.8 plus 0, right? Okay. Well, what do you suppose the derivative of velocity is called? Acceleration. Yeah, the rate of change of velocity with respect to time is what we call acceleration. And wait for this. This is what we call a second derivative of position, the derivative of the derivative. So when you talk about those kinematic quantities, really they're linked by differentiation, okay? What does this tell us about the acceleration? Is it changing?
Yeah.
It's a of t is just negative 9.8. There's no t in that, right? So the acceleration is constant. For physics types, that makes sense, right? The acceleration is caused by the interaction between the bullet and the center of the earth. That never changes, right? Force of gravity acting on the bullet is always the same, right? It's losing velocity at a rate of 9.8 meters per second on the way up. Every second, its velocity is diminishing by 9.8. But that quantity stays the same. Okay? How about that? Right? If I were to graph this thing, well, never mind. Gives you something to think about. Does that help kind of put the kinematic stuff in perspective a little bit?
Yeah.
Yeah. I mean, you guys you're using kinematics equations, so I will derive all those for you. When we do, I'll let you guys do it. When we do the opposite, go the opposite direction in calculus, when we anti-differentiate, so when we start with a function and we work backwards to see what would we have had to differentiate to get that, that's how you can develop, just from measuring the constant acceleration of gravity, you can solve the simple differential equation and come up with all the kinematics equations just like that. That's pretty cool.
Because on the first one you use like the negative 16,
Mm-hmm.
so that one threw me off. 'Cause that
Okay,
was
yeah,
just
because
following.
because
But once we got using like the negative 4.9 squared, I understood that.
okay, gotcha. We'll do more. I wasn't actually planning on doing that today. I was planning on doing something else, but I got the sense people didn't want more homework, so
No.
Are we getting a test today?
The second equation we did made a lot.
okay.
The first one, since it was a different number than 9.8, I was like,
Okay, because the
That
acceleration of
threw me.
gravity is it's negative 9.8 meters per second squared, negative 32 feet per second squared. okay.
Yeah.
Yeah, that's why, yeah.
Do you think it's okay if I like take a week off from retesting?
Absolutely.
Okay.
Yeah. No, do that. I think that's a good
Really
idea.
stressful.
I think that's a good idea. Yeah. Yeah.
If you can write me a letter.
I'd love to. Send me an email, and then when I get just in the subject, just put letter of recommendation. And then give me the deadlines and stuff like that, and I'll put it into my special folder on there.
I need to bring you like my resume or like my activity chart.
Yes, that would be great. A resume, if you've got one. Do you have an activity chart made?
I do.
Okay, if you already have one made, great. But then the other thing I would like is a transcript.
Transcript?
Yeah, okay.
I can get you one. Do you want one like in hand or do you want one like?
Oh, I don't care.
Okay.
You can just email it to me or have somebody email it. I don't care. You can either give me a hard copy or email one. That's fine. I don't care. Either way, I'd love to.
Thank you.
Huh? Yes, you can. I hope you may for sure.
Oh, yes.